So let's continue learning about trigonometric functions. Can we find the sine or cosine of angles that are bigger than 2 pi or just don't look like standard reference angles? Well, 3 pi, notice, 3 pi, there we go, is 2 pi plus pi. So what angle does that represent? 2 pi, remember, is go all the way around. So here's 2 pi. Then do an additional pi. So the angle 3 pi actually points directly left. It points to the same place as pi does because that complete rotation of 2 pi doesn't really do much. And we already know the coordinates of this point are -1, 0 because we're on the unit circle. So straight left just has a negative x coordinate but a 0 y coordinate. And then I would say, what's the sine of 3 pi? It's the y coordinate of that point, which is 0. Okay, so similarly, can you figure out where -270 degrees points? Okay, so here is exactly what we just did. For part B, -270 degrees, since it's negative, we go in the opposite direction, but I have 90, 90, 90. I have 3 full quadrants, so I'm now pointing straight up to the point 0, 1. So what's the cosine? It's the x-coordinate, which is also 0. How about a value of an angle which is not a quadrantal angle? Okay. Can we find the exact values of sine, cosine, etc. of 45 degrees or pi/4 radians? So now, here's the unit circle. Oh, that's a bad circle, but I'm not very good at drawing. 45 degrees points this way. So here's my angle of pi/4 radians. How can I possibly find the coordinates of this point? Now, sometimes when we get to this point in the class, and we're actually like in class talking to each other, someone will volunteer, it looks to be 1/2, 1/2. However, that's not on the circle. How do I know that this point is not on the circle? What's the distance to the origin? Remember, the origin has coordinates 0, 0. So the distance would be the square root of 1/2 minus 0 squared plus 1/2 minus 0 squared. 1/2 squared is a quarter. A quarter plus a quarter is a half. The square root of 1/2 is root 2 over 2, which is about 0.7. What it isn't is 1. And to be on the unit circle, your distance to the origin would have to be 1. So 1/2, 1/2 is actually more like here. It's not on the circle. So 1/2, 1/2 is not on the circle. So no, those are the x and y coordinates. So how are we going to find the coordinates of that point? So what we need to do is use the fact that this is the line y equals x, a nice symmetric line. And by symmetric, I mean if this angle is 45 degrees or pi/4 radians, then this angle is also 45 degrees or pi/4 radians. So it's cut that quadrant cleanly in half. It's split the x and y coordinate equally. So that means on my unit circle, which has equation x squared plus y squared equals 1, okay, its center is 0, 0. Remember the circle at center HK with radius r is given by this formula. So if h and k are both 0 and r is 1, here's your formula for the unit circle. But now, so we know x squared plus y squared must equal 1. That's true everywhere on the circle. At this point, I know that x is going to be equal to y. So therefore, x squared plus x squared is equal to 1. That's 2x squared is equal to 1. X squared is 1/2. X is the square root of 1/2, which is root 2 over 2. Okay. So that is the x coordinate. It's also the y coordinate. So what is the sine of pi/4? It's the y coordinate, which is root 2 over 2. What is the cosine of pi/4? It's the x coordinate, which is also root 2 over 2. What's the tangent of pi/4? It's the y coordinate over the x coordinate, but they're equal to each other, so the tangent is exactly 1. The cotangent is also 1 because it's just x over y, but they are equal to each other. Okay. What is the secant? It's 1 over the x coordinate, which works out to be exactly root 2. And the cosecant, well, since the y coordinate is the same as the x coordinate, 1 over y is the same as 1 over x. It's also root 2. Okay, I'm going to clear out my work so we can finish up theirs, but I also want to do this another way. So let me just quickly show you how they complete the same work we just did. Okay, so x and y are both root 2 over 2, from which we get the sine, the cosine, the cosecant, the secant, the tangent, the cotangent. And this is all the stuff we had just done on the previous slide. I'm going to take advantage of some empty space on this slide, however, to do it a different way. All right? I'm going to zoom in just on this first quadrant picture. So here's the unit circle, nice and zoomed in. And we made this angle of 45 degrees, or pi over 4 radians. Now what I want to do, this point has coordinates x, y. Okay? So pretend you drop this vertical segment here. What are the coordinates of that point? So here's the origin, it's 0, 0. This point has coordinates x, comma, 0. I move straight right x units, and from there I'm going to go up. So the length of this side is x, and the height of this side is y. What about the hypotenuse of this triangle? What's this length? It's a radius of the circle, which is exactly 1. Also, I went vertically down to the axis. I made a right angle. Okay, so what are the other angles in this triangle? Well, the angles of a triangle, add up to 180 degrees or pi radians. So I'm going to work in radians. This is pi over 4 radians. A right angle is pi over 2 radians. So this angle is what I don't know. I'll call it theta. So the unknown angle plus the pi over 2 plus the pi over 4 must equal the full triangle, which we know is pi radians. 180 degrees is pi radians, remember. So if I subtract this and this from both sides, we get pi minus pi over 2 minus pi over 4. Well, what's pi minus pi over 2? If I had a pi and I took away a half a pi, what do I have left? Half a pi. If I had half a pi and I took away a quarter of a pi, what do I have left? A quarter of a pi. So this angle is also pi over 4. So now notice I have this angle and this angle are equal. What do we call a triangle with two equal angles? Isosceles. And what do I know about the lengths across from those angles? They're equal. So since these angles are equal, the side across from the angles are equal, x equals y, and from there we do all the same work. Okay, so you didn't have to rely on some sort of symmetry about this line. You can work through using geometry as well. Okay, once you know x equals y, you just do all the same steps that we had. This was already there. Okay, so let's keep going. Now things are getting a little trickier. Can you find the exact value of each expression? So I'll do the first one, all right? Cosine of 45 we actually already did. It was on the previous slide. Cosine of 45 was exactly root 2 over 2. Root 2 over 2, sorry about that. What about the sine of 270? We did figure this out in an earlier example, but maybe we forgot. That's fine. Take your unit circle. Starting from the positive x-axis, mark an angle of 270 degrees, which is 90 degrees, 90 degrees, 90 degrees. Pointing straight down is 270 degrees. The coordinates of this point down here are 0, -1. The sine of an angle is the y-coordinate, so the sine of 270 degrees is -1. What's -1 times root 2 over 2? Negative root 2 over 2. So really all you have to do part B and C is find each of these things individually and then simplify everything down. So pause the video and try to work through this. Okay, so let's take a look. So let me clear my pen marks out of the way, sorry. So yes, as we saw, the first one is just root 2 over 2 times -1, which is negative root 2 over 2. The cotangent of pi over 4 is 1, and the cosine of 3 pi over 2 is 0. So you end up with 1 minus 0, or 1. Cosecant of pi over 4 is root 2, which we had done just on the previous slide. And secant of pi you can work out to be -1. Now root 2 squared is just 2, and I have a -1, so for an end result of 3. Okay. Moving on. How about 60 degrees or pi over 3 radians? Can I find sine, cosine, tangent, cosecant, secant, and cotangent? So here, we're going to use a bit of geometry as well. if I do the same little trick of marking off an angle of 60 degrees, then dropping an altitude, I know this is the x coordinate and this is the y coordinate of this point, and I know the radius of the circle is 1. So this is a slightly zoomed in picture that we had over there. Okay. But since the angles add up to 180, I know the missing angle is 30 degrees. We might recognize this from geometry as a 30, 60, 90 triangle. And the 30, 60, 90 reference triangle I always remember is this. 1, 2, and root 3. Okay. But notice the hypotenuse here is 1, whereas on the reference one that I always remember, it's 2. So the triangle we have in the unit circle is half as big, which means x needs to be half as big, it's a half, and y needs to be half as big, it's root 3 over 2. So that's where they're getting x and y from. Okay, just remember your reference triangles. So the standard reference triangles are your 45, 45, 90, which in the previous example of a 1, 1, and root 2. And if I want the hypotenuse to be of length 1, I just need to divide by root 2. Okay, and this is from the previous work. So this is your isosceles right triangle. Your 30, 60, 90 triangle, the standard one I usually remember is 1, 2, and root 3. And if I want the hypotenuse to be of length 1, I just divide everything by 2, and you end up right here. So now we know the x and the y coordinate, which means we can find the sine, cosine, etc. quite quickly. Oops, sorry. So they're just stating here that, yes, 60 degrees or pi over 3 radians corresponds to this point, 1/2 comma root 3 over 2, from which we get the sine is the y coordinate, so the cosine is 1 over, so cosecant is 1 over that. The cosine is the x coordinate, so the secant is 1 over that. The tangent is the ratio of the y to the x coordinates, and the cotangent is the ratio of the x to the y coordinates. So we managed to find nice exact values for the sine and cosine, etc. of 60 degrees. What about 30 degrees? This is very, very similar to 60 degrees because we get to use the same reference triangle. It's just the long side is on the bottom rather than going up. So instead of 1/2 root 3 over 2, it's reversed. It's root 3 over 2 comma 1/2. It's still the 30, 60, 90 triangle. It's just I put the 30 angle as pointing to the right rather than the 60 degree angle. But again, now that I know my x and y coordinates, root 3 over 2 and 1/2 respectively, we can just blast through and say sine, cosine, tangent, cosecant, secant, cotangent. The sine is the y coordinate, 1/2. The cosine is the x coordinate, root 3 over 2, and then use all the other definitions to fill this in. After which, we have this nice chart here. So on a previous slide, we had the quadrantal angles. So we already know how to deal with 0, pi over 2, pi, 3 pi over 2. Okay, that was a previous slide. It filled in this chart. Now we can also fill in these ones right here. And again, don't try to memorize this. I haven't. Okay, 45 degrees I tend to remember because the sine and cosine are the same, so it doesn't matter if I get them backwards. The pi over 6, the pi over 3, I always have to think for a second which one is which. I have not memorized this chart. I just remember that the relevant quantities are going to be 1/2 and root 3 over 2, and then just based on visualizing in my head, for 30 degrees, x is bigger than y. Therefore, for 30 degrees, the x coordinate, root 3 over 2, is the big one, and the y coordinate is the small one, 1/2. But for 60 degrees, the y coordinate is going to be bigger than the x coordinate. It's taller than it is wide. So for 60 degrees or pi over 3 radians, the big number, root 3 over 2, is my y coordinate or the sine. And the small number, 1/2, is the x coordinate or the cosine. I genuinely think that every time these things come up. Okay? I have not memorized this chart. Math is really not about memorization. Okay, so that'll finish up this video. We've determined sine and cosine and the associated other functions for a bunch of angles, the quadrantal angles, and then also 30, 45, and 60 degrees, aka pi over 6, pi over 4, and pi over 3 radians. In the next video, which will be the last one in this section, we'll come and we'll do various word problems.